Hey guys, Mr. P. In this video, we're going to talk about the global climate system and what that really entails. We're going to talk about the difference between weather and climate. We're going to talk about how all of these weather and climate patterns help to shape Hey guys, Mr. P. In this video, we're going to talk specifically about the global climate system. We're going to talk about how weather patterns help to shape an individual location's climate. We're also going to talk about how ocean currents and wind currents are established and what those currents mean for not only weather patterns but individual climates. And we'll close out with some of the specific events that lead to this global climate change. So, what is the difference between climate and weather? I've heard several people use these two terms really interchangeably, and they are very different. Weather is the day-to-day specific events, the precipitation, the clouds, the wind, the temperature, the short-term fluctuations in all of these variables, the minute-to-minute changes, it being sunny 1 minute and 47 degrees to it being cloudy and 38 degrees. These day-to-day, minute-to-minute, short-term events constitute weather. On the other hand, when we take individual weather events that establish patterns or define patterns and averages over the course of many years, that gives rise to an individual's climate. Now, climate is established not only by these patterns or averages of the temperature, precipitation, clouds, wind, and other variables. It also has a lot to do with the latitude. Okay, you'll notice that when you look at this right picture, that the different precipitation bands or the different temperature bands associated with this type of graph or this type of model helps really show what latitude from south towards the equator and north towards the pole really does to the distribution of those temperatures. The temperature and the average temperature is really influenced by latitude, which is the degree north and south of the equator. Next thing we need to talk about is solar energy and the greenhouse effect. So what is solar energy? Solar energy is the energy that is emitted by the sun. That energy is in two forms. It is in visible light that allows us to see. It also is in invisible light, meaning UV radiation. That is the type of energy that will produce sunburns if you're outside and exposed to the UV radiation for too long. But basically, this sunlight, visible light, and UV radiation is going to permeate through space. It's going to pass through our atmosphere. It's going to strike landmass, specifically the hard landmass. And it's going to lose energy upon impact. And you'll notice that it shifted from this kind of really intense, really short wavelength yellow band to this longer wavelength red band, which is lower energy. This model is designed to depict energy levels. The yellow is more energetic and the red is less energetic. Some of this energy, a small percentage, can re-radiate back into space, but the large proportion or a large proportion of this energy is actually going to get trapped within the atmosphere and re-radiate back down to Earth. It's this trapped heat inside of our atmosphere that helps to warm the Earth and gives rise to temperatures that are conducive to sustaining life. That is the greenhouse effect. It's no different than when you sit your car in a parking lot exposed to the sun with glass windows. It's always hotter inside your vehicle than it is outside, and that's because solar radiation can pass through glass, but then upon hitting the dashboard and the seats and the seat belts and the floor, can't re-escape that glass, and so it gets trapped inside and it gets warmer, and so that is a greenhouse effect. This retention of heat leads to an unequal distribution of heat between the equator and the poles. Obviously, if you know anything about geography, you know that it is colder in the poles. The North and South Pole are cold year-round. And you know, or should know, that it's warmer in the equator year-round. So there is an unequal distribution of heat on our planet, and it's that distribution or unequal distribution of heat between the poles and equator that helps drive A lot of our climates and our weather patterns, which give rise to long-term climates, and helps drive not only the wind but the ocean currents as well. So, Earth's average temperature is mainly controlled by the concentrations of three gases in the atmosphere. That's carbon dioxide, methane, and water vapor. We're going to look at that on this picture. You'll see that when you look at the right side of this image, you see that there is CH4 molecules, the green ones. Those are the methane. You have little water drops, which are blue, which is H2O. That's a gas form of water. We call it water vapor. And then we have these yellow ones, which are supposed to be CO2. So 3 greenhouse gases, which are highly concentrated within the atmosphere. And the way global warming happens, or the contributing factor to global warming, or the retention of heat, or increased retention of heat, is that as these greenhouse gases increase in concentration, meaning we're emitting more CO2 through combustion, we're emitting more CH4 or methane through livestock production, a lot of these gases are going to be increasing in concentration in the atmosphere, and if they increase in concentration, it's going to trap more heat because less heat is able to escape. As this heat re-radiates off the surface of a warmer planet, it's going to bounce off of these molecules, which are increasing in concentration in the atmosphere, and it's going to help hold that heat in. So the greater the concentration of greenhouse gases, the greater the heat retention of our atmosphere. That is global warming. These gases naturally leave and enter the atmosphere as they move through their respective geochemical cycles. There is a carbon cycle, which would include methane. There is a carbon dioxide component to that carbon cycle as well. And then water, there is a water cycle in terms of the addition or individual geochemical cycles. Concentrations can be affected by non-human and human causes. There are a variety of non-human reasons why these concentrations might be fluctuating. There are also human activities like combustion. Gasoline combustion engines are increasing the CO2 emissions in our planet. If changes in these cycles increase the greenhouse gas concentrations, the atmosphere retains more heat and Earth warms. If the changes that happen on the planet decrease greenhouse concentrations, more heat will escape, and therefore the Earth will cool. This obviously doesn't happen overnight and takes a long time to do. Now, the unequal distribution of heat on our planet is not just tied to latitude, but it is also tied to the tilt, or the Earth axis. We know that the sun rays coming in from the side of this particular image is going to strike the Earth on a more direct line from the equator all the way to basically throughout the temperate zones. Now, I like to point your attention to the equator. The equator is our 0 spot, that's 0 degrees, and then we can go north to a 23 degrees north, or 23.5 degrees north, and we can also go south of the equator to 23.5 degrees. The Tropic of Cancer and the Tropic of Capricorn are our southern and northern limits of this center band that is called the tropics. Everything inside of the Tropic of Cancer and Tropic of Capricorn would be considered the tropic zones. Everything from 23.5 to about 66 degrees would be a temperate zone. We in Kansas live within North America, which is located within that northern temperate zone. So we get this more direct line of sight in terms of more direct sun exposure during our summer, which is in kind of that May, June, July time frame. Southern hemisphere, like Australia, is kind of half in that tropics, but also half in that temperate. So 23.5 degrees south to about 66 degrees south would be that lower or southern temperate zone. Again, they would get the direct sight of the sun, or more direct path, during their summer, which would be our winter. So in that like November, December, January time frame. Okay, Earth's climate zones are produced by unequal distribution of the solar energy across Earth's surface. The tilt of the Earth's axis causes this distribution to change over the course of a year, resulting in the seasons. So as it warms in our location and it becomes summer from spring, we are getting more and more tilted towards the sun. And then as we progress through fall and then into winter, we start kind of positioning ourselves, or the Earth starts positioning itself away from the sun in the northern hemisphere. And then the southern hemisphere would be exactly opposite. So what does this unequal distribution of heat between the poles and the equator do for the global winds? We know that hot air rises and cold air sinks, and that's because it changes the density. The warmest spots of Earth are always around the equator, which means that's where a lot of our air warming takes place. You'll know that if you look at this on kind of its cross section, that air right at the equator is going to rise up higher into the atmosphere, and then as it cools, will start settling down closer to Earth's surface. And then it continues to do that. So there's kind of this upwelling of hot air rising, cold air sinking. Now it's also important to note that this unequal distribution of heat creates these wind and ocean currents, which we'll talk about. There are trade winds both in the northern hemisphere and southern hemisphere that not only are impacted by the rotation of the Earth, but they're also impacted by these unequal distribution of heat. So air that is heated in warm areas, such as around this equator, are going to expand, become less dense, and therefore rise. As the air rises, it spreads north and south, losing heat along the way. As it cools, it becomes more dense and therefore sinks back closer to the Earth's surface. And as the air travels from places where it sinks to places where it rises, it creates wind. Wind is just air moving from an area of kind of high pressure to an area of low pressure. As the Earth's air increases in temp, it becomes less dense, and as it decreases in temp, it becomes more dense. And so as air becomes more and less dense, it becomes more highly pressurized and more lower in terms of air pressure, and so it moves from place to place, creating this wind. It also is important to note that because the Earth rotates on its axis, it causes the winds to blow from west to east over both land and sea in the temperate zones, and from east to west over the tropics and the poles. So we are residing in Kansas, so we're right in the middle of the country. And so our kind of natural trade winds in the temperate region of the northern hemisphere blow west to east. So our winds typically come, or our trade winds typically come from west to east. If you were to drop straight south into this tropic zone, you'll notice that the trade winds run east to west. The Earth's rotating around the axis in the exact same way all the way around the Earth, but based on where it's at on the planet dictates the direction that those trade winds are in, which is pretty interesting. If we look at more of a kind of stop focusing on the wind currents and we kind of translate back into ocean currents, you'll see exactly the same thing. You'll notice that on this map, which is 2D, you'll see that there are a variety of red arrows, and there's also a variety of blue arrows. Red arrows indicate warm water, blue arrows indicate cold water. You'll also notice that there are typically always red and blue arrows associated together. So these warm currents and cold currents are kind of paired. So in this Atlantic Ocean, you'll see that there is a Gulf Stream, which is warm water, and there's this Canary, which is cold water. And it kind of creates this mixing here. Same thing on the west coast of the US. You've got warm water and cold water both in the same place. So these ocean currents are really shaped by patterns of warming and cooling, and by winds moving not only across the surface of the water, but also the surface of the land. Prevailing winds blowing over the ocean create surface currents that profoundly affect weather and climate in coastal areas, and cold ocean water near the poles sinks and flows along ocean floor, which is called upwelling, which I kind of alluded to in the previous slide. But this upwelling can intensify when prevailing winds push surface water away from the continent, and you see that because if you recall from the last slide, that in this tropic region, winds blow east to west. So the prevailing winds are going to be blowing across this landmass and actually pushing the surface water away from the continent. That mixed with this current that is kind of coming in through here and moving away, as well as the upwelling, that's going to create very intense weather patterns. And it creates a phenomenon called El Nino, which you've probably heard about, which greatly impacts the local weather patterns not only in this area of South America, but it actually also impacts greatly the local weather patterns across the southwestern United States, all the way across this Pacific Ocean, and impacts places like Australia and Indonesia, which you can see clear over here. Just from the prevailing winds moving over this landmass in tandem with the upwelling that happens in the ocean and ocean currents can greatly impact the precipitation amounts all over the globe. So, last concept that we need to talk about is this idea of rain shadow effect. The reason we talk about it within this kind of context is it is part of the geosphere, which also impacts the hydrosphere because we're talking about water. And it also talks about weather patterns and local climate. Now, this is Washington State. Washington State is a good example of the rain shadow effect, and it's also a good example of how regional climates are shaped by latitude and the transport of heat and moisture by winds and ocean currents, and by the geographic features such as mountain range, large bodies of water, and ocean currents. So this has everything that we need to talk about, kind of the perfect storm, so to speak. So Washington State is bordering the Pacific Ocean. So everything over here is the Pacific Ocean. Those trade winds are moving east to west, and so the trade winds are moving from the ocean inward into Washington and hits this mountain range that runs right up through kind of the north to south border of Washington State. It creates a situation in which the water-rich air, or the very humid air, creates or hits this boundary of really high elevation, and because it's cooler and more humid, it causes all of the precipitation to fall on the western side of that mountain, and therefore takes all the moisture out of the air before it can transport itself inward or eastern, and therefore becomes very dry on the eastern side of that mountain range. So, same latitude. If I just draw a line right through this is the same latitude, meaning it should have relatively similar climates. It should have relatively similar temperatures. It should have relatively similar weather patterns. But it doesn't, all because of the mountain range, which is the geographic entity. So Western Washington, climate-wise, is cooler, it's more humid, and has a lot more precipitation simply because of the mountain range and the prevailing winds that are moving from the eastern shore, or I should say the western shore, inward towards the east. Eastern Washington is very dry, it's very hot, and it is due to that rain shadow effect that I just talked about. Things that change climates, there are 6 of them as examples that we'll focus on that are involved in extreme changes in not only temperature, clouds, winds, patterns, and amounts of precipitation, and frequency and severity of extreme weather events. And these 6 specific things can greatly impact the way that weather and climate shape a particular place. Things like changes in solar energy. People typically talk about global warming as an issue related directly to the emissions of greenhouse gases, but we can see by looking at solar energy data that solar energy actually progresses in cycles. Okay, going back to 1980, we've had roughly 3 or 4 solar cycles where there is an intensity change or an intensity shift in the amount of energy being emitted by the sun. And so because the intensity of the sun is changing, it can greatly impact the temperature or the amount of winds or the ocean currents, because temperature drives, or the unequal distribution of those temperatures can drive the solar conditions and therefore drive the ocean and wind currents. Variations in Earth orbit. Earth, whether you know it or not, does not follow the exact same path. It actually gets wider and narrower on its way around the sun. Over the course of 100,000 to 413,000 years, it has shifted in its actual orbit. As it gets closer in its orbit to the sun, it's going to have a greater impact on the heating that sun can cause on the planet. As it gets farther, it's going to have a profound effect as well. So just the Earth's natural variation in its orbit can impact climate. Meteorite impacts can greatly impact Earth's climate because it can impact the ejecta that gets sent into the atmosphere. And as different impact material gets put into the atmosphere, it can block sun out. It can also hold heat in. Changes in distribution of continents and oceans. So we know that since Pangea, our continents have been moving and continually move through forces like plate tectonics. And as those move, it will impact ocean currents. It'll impact the way that the globe is heating. It impacts the distribution of those land masses that can also impact the way that we retain heat. Mountain building, we know that we're continuously building more and more mountains as those plate tectonics move, the plates underneath each other. We cause more and more and more mountains, and our mountain ranges are typically getting taller. Again, it can impact the way in which our climate is impacting local weather patterns. And then we have volcanic activity. We know that as volcanoes spew lava, as they erupt, they can deposit this rock. And as new islands emerge through volcanic activity, it gives rise to more landmass, which can heat, which can also impact the way that the Earth retains heat. So these are 6 ways in which things out of our control impact changes in our climate. This global climate change might not necessarily be all human caused, but more data is needed. That's it for this video. If you learned something, give it a thumbs up. If you have any questions, bring them to class. See ya.